Hello everyone, my name is Bing Yang. I'm a material scientist working in the field of computational material science and autonomous synthesis. This is my channel for sharing my understanding of material science. I will post either my understanding of a paper, some mini tutorials of material science, as well as some funny things as a material scientist. Please subscribe if you want to get up-to-date video from me. Currently, I'm a postdoc working with Professor Gerben Cedar at the University of California, Berkeley. So today I'd like to show you with some of my experiences of studying short triangle order and lithium transport in fluorinated disorder Rocksalt cathode material. All the details of this video can be found in these two published papers in Advanced Energy Materials as well as CHEM. Alright, let's get started. If you work in the field of lithium-ion batteries, you may be familiar with this kind of layered materials, right? So there's a very funny story about the layered materials because after spending so many years trying to find the best chemistries as the layered materials, we sort of realized that the only thing works has to go with N, M, and C, which N represent nickel, M represent manganese, and C represent cobalt. The reason is because all the other elements tend to migrate from the transition metal layer to the lithium layer, so that it's gonna block the lithium diffusion pathways. However, these three elements are not so friendly, because manganese does not really contribute to the capacity when it's 4+. At the same time, cobalt is very expensive and is very limited in production. Nickel looks promising in terms of the redox capability, but the nickel-rich materials tend to have a significant tendency of densification on the surfaces, which also gonna prohibit the performance of the materials. Those kind of effects actually drives the discovery of the disorder Rocksalt cathode materials. It's a materials which is similar to a layered materials, but the difference is that you have a random distribution of the lithium and transition metals in the cation lattices. So in that case, you don't really need to worry about the transition metal migrations because there's not even a transition metal layer. With this kind of a design, you can use pretty much everything in the periodic table as long as you can make them. And instead of diffusion in this 2D plane, the lithium transport in such materials only rely on some local structures, which we call 0TM unit. It's a tetrahedron made of only lithium ions. In order to make sure this cathode material is gonna work, we want to make sure that we have enough of this 0TM unit so that it can percolate through the bulk. The design strategy is very straightforward, right? So statistically, we want to increase the amount of lithium in the materials so that we can have enough of this 0TM unit. So we just need to go lithium excess. However, this lithium excess, these other Rocksalt materials, is not perfect because the retention is not so good. It's kind of obvious if you look at the chemical formula. Like here we go lithium excess, right? So we have to charge compensate in the analysis by putting some high valence metals, which are usually redox inert. So at the same time, we're sort of sacrificing the transition metal redox capacities, right? So we end up with a lot of irreversible oxygen redox. Fluorination can be a solution to this, because fluorine actually have a 1- at the anion, so it actually reduces the average cation charge state required to charge compensating. So we can utilize more transition metal redox. In the past few years, people are really trying to design all sort of oxyfluorides that can reach both high capacity and high retention. However, we have very few knowledge about it. 6 years ago, we started to establish the theoretic picture of how disorder Rocksalt works. We know that we have to go lithium excess, right? But lithium excess does not really tell us does not really tell you everything. Here I show you two lithium excess disorder Rocksalt materials. The first materials is lithium manganese zirconium oxide, while the second one is lithium manganese titanium oxide. Both of them have the same amount of lithium excess, and they use the same amount of redox centers, which is manganese 3 plus to 4 plus, but they show very different electrochemical performance. And if you do a characterization on those materials, you will realize that the LMZO actually have a very interesting diffusive patterns, which looks like a diamond. And on the other hand, the LMTO have diffusive electron diffraction patterns, which looks like a ring. So this is an indication of short-range order that happening in these disorder solid solutions, which sort of ring the bell that the short-range order is the key to manipulate the performance of the materials. So in order to understand the influences of short-range order, we actually develop our computational work in 3 steps. The first step is actually to establish some physical pictures of the short-range orders, followed by some accurate structural models which really can reproduce the short-range order features we see in experiment, and then we can use these structures to predict the performance of the dissolved rock salt materials. So first things starts first. So what is the physical picture of short-range order? There are basically 2 things that influences the short-range order. The first thing is the cation mixing, right? Because the short-range order diffusive pattern is essentially a Fourier transformation of the short-range order parameters on the cation side. So it's really decided by how lithium is mixed with transition metals. At the same time, the anion actually also matters, because the oxygen and fluorine distribution can indirectly influence the cation mixing. So let me show you some schematic pictures. So here we want some good short-range order, which looks like we have lithium-rich environment and lithium poor environment. At the same time, we want the lithium-rich environment to percolate, right? However, if we increase the size of transition metal, they will become similar with lithium, so they tend to mix with the lithium. So in that case, in every single tetrahedrons, we prefer to have coexistence between lithium and transition metals. So in that case, we have less chance to observe a 0-TM channels. At the same time, the charge also matters, because a lithium iron have 1+ charge state, right? So if you have a 3+ transition metal ions, they prefer to mix with the lithium. So you can reach an average 2+ at the cation site. So in that case, when you have a lower charge state, it's actually prohibited mixing between lithium ions with transition metal ions, so that you can have you can transform from the bad short-range order to the good short-range order. At the same time, the anion also matters, right? Because we found from the experimental observations of NMR that the fluorine really want to bond with the lithium. So they form this kind of lithium-rich environment, which is either lithium-6 fluorine or lithium-5 metal fluorine, which can be verified by these diamagnetic signals. So this basically indicates that the fluorine will initiate lithium-rich local environment in the lattice. So how to capture this? In order to capture this, we should be able to simulate this kind of a local structure environment, right? So in order to achieve this, we first need to do advanced DFT calculations on a collection of configurational space. So there are infinite configurations in a random solid solutions. So we have to sample enough of them so that we can build a classic expansion model, which is kind of a machine learning model which maps the configurational space with the energetic space. With this kind of a model, we can further do a very cheap Monte Carlo to sample a very large cell and sample the equilibrium configurations that are gonna stabilize in a given temperature, right? So in that case, we can use those structural models to simulate what we see in experiment. So typically, we do electron diffractions, we do PDFs. So we can also do electron diffraction and PDF simulations on those short-range order structure generated from computational models. And from this kind of a framework, we know that in a random structures we only have this long-range diffraction pulse. So we simulate the random structures using this framework and have a consistent observation of a random lattice with only long-range ordered pulse. At the same time, we are also able to reproduce what we see experiment. For LMTO, we observe this kind of ring-like patterns, which can be confirmed by the simulated electron diffractions. And at the same time, the LMZO, we have these diamond-like patterns, which can also be confirmed with the simulation results. So now we have theoretic tools that can reproduce what we see in experiment in the 3D atomic structures. So in the next video, I'm going to show you how do I use this model to predict the performance of the materials and how does that compare with experimental observations. So thanks again for your watching. I'll see you in my next video.